few things on this before, actually. What we're going to look at again is easy water. It's really interesting stuff. It's a bit fringe, which kind of makes it a bit sort of, well, exciting actually, to be honest. Now, it was first looked at by a guy called Pollock, so just stick that in your Google Scholar search. You'll come up with loads and loads of information, research papers and bits of work that people have been doing, including a very good TED talk on this stuff. Now, easy water is a really interesting idea, because if you think about the structure of water when it's actually liquid, it's fairly disorganised and actually has quite a lot of space in between it. And when you freeze it into ice, you get kind of like a cubic structure, so still you get a lot of space in there. But as it goes from water to ice, it adopts a kind of helical structure, where it lays one on top of the other and twists out. And that structure is so tight, it is supposedly able to squeeze out any ions that might otherwise be in there. At least that's the idea. Now, because we want to look at easy water as a possibility for desalination, and maybe even to run a solar cell from it, then we want a bit more of a test to see, hey, what's going on here? Is this actually real? Now, easy water structures itself like this. If you have a drop of water on here that you've mixed up with a salt solution, and you pop it on a plate, and that plate is usually something that's hydrophilic, then the idea is that those helixes will form at the boundary of the plate and the boundary of the water. And it creates a compressed zone where all the solute ions are forced out. And that compressed zone, Pollock called the EZ zone. In this zone, there are no ions, apparently, okay? And they all get rammed up into this solute zone here, where they all now actually sit. So that is the basics of what he's talking about. Now, nobody uses a hydrophilic plate. I think Nafion was one that he used. But we did a bit of reading about this. Actually, Steve did a bit of reading about this. And it turns out that Nafion isn't the only thing you can use. Actually, surprisingly enough, you'll get this effect in certain kinds of metals, particularly zinc. So we're going to use a zinc plate to try and test this idea. Now, it's really obvious what we ought to be testing, because DI water, or water with no ions on, has an infinite resistance. It won't conduct. Whereas if we can increase the amount of ions in the solute zone, then obviously the resistance is going to drop. So say we take a standard solution and we measure the resistance of that solution, it'll have some fixed value. And we then drop it on our plate, and we put a couple of electrodes in here to measure resistance at a fixed distance, and a couple of electrodes here to measure at the same fixed distance to measure the resistance, then obviously what we should see is that that resistance will go up markedly, and this resistance will go down markedly. And we're going to take that as kind of a proof, if you like, that the EZ zone is going to form. Now, that's really cool, because the EZ zone formation creates a potential difference between these two zones. Pollock says that the driver for that is actually sunlight. So if we shine sunlight on this, that EZ zone will grow. If we then draw a microamp current from it, because in a small experiment that's what we're able to do, that EZ zone will collapse. So the sunlight becomes a driver for a potential difference within this. And there stands a possibility then of being able to capture that in terms of a solar cell. And we're quite excited about that. There's also something else that's really quite exciting. That if you put a little pipette in there, for example, you'll be able to draw off that water. And the sunlight will drive that by creating the EZ zone as you suck it off. So there's a possibility there of sunlight-driven rapid desalination. That's kind of why we're interested in it. But like I say, it's a bit fringy, so we thought we'd have a look at that first. Now, Steve has designed an experiment. And in a minute we're going to look at that experiment, and it's pretty simple really. We've got a plate here, and then some distance there, we have two electrodes facing in, and we can take a resistance measurement from those two electrodes, as long as that distance there is round about 100 micrometers or so, something like that, because this EZ zone is supposed to form on zinc somewhere between 100 and 200 micrometers. So we should be more or less in the middle of the EZ zone there. Then we put some kind of insulator there, and then directly above that we have another double set of electrodes, so that that distance there is going to be greater than 300. So that we're outside of the EZ zone, and again we can take an ohmic reading of that. And what we should see is that this one will go up, and this one will go down if that EZ zone is being formed. And that's the experiment Steve's going to do for you.
So his experiment we drew on the board is just vertical instead of horizontal. And look at these two figures. Wow. Okay, so the two outer contacts you can see here are connected to Steve's display. The two inner contacts are connected to this meter here. This is reading in mega ohms, as I said, that's reading in kilo ohms. So this is 793 kilo ohms for the inside ones, 196 kilo ohms for the outside ones. Now you see the spacing of the two outer wires there. It's somewhere around 4 times the distance between those two wires and that wire there. Now distance is related to resistance. If they're further apart, they should show more resistance. Now they don't. This is somewhere around 4 times less than that one, with a wider distance. So it's an interesting observation there anyway. Anyway, let's go on and I'll show you exactly how we put this all together. Okay, a closer look at it's a very simple experiment really. I've laid some masking tape underneath. Position those two in the centre. You might be able to pick out that they're very close to the zinc plate. Laid some more tape over there, over the top, and then after 4 or 5 layers of tape we put the two outer ones on the outside, and you can see they're further off the plate than the two in the middle. So that's detecting the EZ zone, the two in the centre, and the two on the outer are detecting the zone which is full of solute. Okay, so there's the figures. This is the experiment. It seems there may be evidence that there is an EZ zone there. What we plan to do now is look in more detail and perhaps construct a more robust experiment, and we'll keep you posted, keep you up to date.